Welcome to Logarithms by Professor Charles Dorner. Please like, subscribe, and share this video with your friends for more content. The logarithm is the exponent or power to which a base must be raised to produce a given number. X is the logarithm of n to the base b expressed mathematically. For example, 24 equals 16. Therefore, 5 is the logarithm of 16 to base 2, or 5 equals log 216. Similarly, since 103 equals 300, then 3 equals log 1030. Common, or Briggsian, logarithms are those with a base of 10, and they are denoted by the notation log n. Logarithms were invented in the 17th century to speed up calculations. They drastically cut down on the time needed to multiply numbers with many digits. For over 300 years, they served as the backbone of numerical work before the development of mechanical calculators in the late 19th century, and computers in the 20th century rendered them unnecessary for complex calculations. However, the natural logarithm, written as ln with base e equals 2.71828, remains one of the most useful mathematical functions, with applications to mathematical models in the physical and biological sciences. Scientists quickly embraced logarithms due to their many practical applications, which made previously laborious calculations much easier. Scientists could find the product of m and n by first looking up the logarithms of m and n in a special table, then adding those logarithms together, and finally looking up the number with the resulting logarithm known as its anti-logarithm. As a mathematical expression, this is given by log mn equals log m plus log n. To find the anti-logarithm 100,000 of 100 times 1000, we first look up the logarithms of 100 times 2 and 1000 times 3, add these two numbers together which equals 5, and then look up the corresponding entry in the table. Similarly, logarithms can be used to transform division problems into subtraction problems such as log m divided by n equals log m, log n. Furthermore, logarithms provide a convenient shortcut for calculating powers and roots. Similarly, any two positive bases can be used to convert a logarithm, except for one, which can't be used as a base because all its powers are 1. Give any real number x and positive real numbers m, n, and b, where b is not equal to 1. We show log base b of mn is equal to log base b of m plus log base b of n. Let m equals log base b of m and n equal log base n. In exponential form, these equations are b to the m equals m and b to the n equals n. It follows that log base b of mn equals log base b times b to the n times b to the n. Substitute for m and n equals log base b times b to the m plus n. Apply the product rule for exponents. Equals to m plus n. Apply the inverse property of logs equals log base b to the m plus log base b to the n. Substitute for m and n. Given any real number x and positive real numbers m, n, and b, where b is not equal to 1, we will show log base b to the m divided by n equals log base b of m minus log base b of n. Letting m equal log base b of m and n equals log base b of n. In exponential form, these equations are b to the m equals m and b to the n equals n. It follows that log base b of m divided by n equals log base b to the m divided by b to the n. Here you substitute for m and n. Next, log base to the b to the m minus n, where you apply the quotient rule for exponents. Next you do m minus n and apply the inverse property of logs. Next you do log base b to the m minus log base b to the n and substitute for m and n. Here you can see log base b to the x squared equals log base b to the x times x, which equals log base b to the x plus log base b to the x, which equals 2 log base b to the x. You'll see that we arrived at a solution for the example above using the product rule for logarithms. The power rule for logarithms, which states that the log of a power is equal to the exponent times the log of the base, has been derived as a result. Remember that even if the input to a logarithm might not be expressed in terms of a power, we might be able to convert it to 1. The logarithm of 1 to any base is always equal to 0, as long as b is positive, but not equal to 1. Here you can see log base b to the 1 is equal to 0. Here, the argument's logarithm, which is enclosed in parenthesis and where the argument equals the base is 1. Here you see log base b to the b equals 1. Here you have log base b to the b to the k equals k. The logarithm of an exponential number where its base is the same as the base of the log is equal to the exponent. A number is equivalent to its logarithm when it is raised to its base. Here you can see b raised to log b of k equals k.